And the other thing is that higher temperature also causes gas molecules to travel faster because they have more kinetic energy, right? Okay, so those two things you keep in mind, and those are the graphs also that are given to you over here. Okay, and so this is the speed, and so at a higher temperature, the gas molecules are traveling much faster, and then here this has to do with the mass of the gas. So helium here travels a lot faster than, say, chlorine. Okay, and so this is a very useful calculation. It may not seem anything to you, but God forbid, again, if we had anything like something of a pores that are released, which could be anything like a biological thing or a chemical gas that is released, which travels at a certain time, and then you have to evacuate a whole town or something, then you can let them know, well, you can evacuate by next day, 24 hours, or 48 hours, because all these gases or molecules will travel at a certain time. Okay, and so you can figure out how long it will take for some spores or some chemical gas to actually spread out. Okay, so that's where this calculation becomes kind of important. Okay, so that's about the speed of gases. And then we have two words here, effusion and diffusion. Okay, and this is just about how gases will mix with each other. Okay, so diffusion is when you cannot tell a pinpoint source of a gas, okay, as to where it's coming from. So it's very hard to tell. Okay, so for example, two gases just merging in the atmosphere, you really can't tell where the source is. In case of effusion, on the other hand, there is a very small area from where the gas can be coming out. And so, for example, when you have pipelines of natural gases, then you can actually pinpoint a location in case there is a leak in the pipe. Okay, and then you can tell that this is where the effusion is from, not diffusion. So you use those different words depending on how the gases are mixing with each other. Okay, so effusion is a little bit easier to locate, okay, and then treat or fix. Diffusion is a little bit harder, okay, because there is no point source for it. Okay, so these are just two different ways how gases will mix with each other. Okay, and then of course we have real gases. Okay, and we've talked a little bit about ideal gases. Ideal gas, in fact, we've been talking about ideal gases only. Okay, so far, ideal gases behave in an ideal manner in the sense how you want them to behave. Okay, and we say that all these gases that we study is usually at like room temperature or at STP, as we say, but the STP, the temperature is 0 degrees Celsius. 0 degrees Celsius is not our normal temperature. Okay, even right now, the temperature is not 0 degrees Celsius. Okay, and thank God for that. Okay, that's why we moved. But in any case, it's not 0 degrees Celsius, which means that the difference between, say, in a freezing versus 25 degrees or 35 degrees is a big temperature difference. Okay, so the gases can behave differently at 0 versus at 35. Okay, however, maybe the difference is very small. Okay, it's not so much. And the same thing happens with the pressure also, whether you're here or 8,000 feet above sea level, maybe you do not feel so much of a difference, okay, with the pressure difference in there. But when you start taking things to a little bit more extreme conditions, then the gases will start behaving differently, okay? So here we're not talking about extreme conditions when you go from here to 8,000 feet high or a 25 degree temperature. No, we can handle that much, okay? That's not a big deal. But when we're talking about going from, say, 273 Kelvin down to about 100 Kelvin, that's a big difference, okay? That's a really low temperature that you're going down at. And then when you change the pressure, okay, too much, that's when you have gases behaving a little weird, okay, in there. So they're not like what we call ideal gases anymore. They're going to be what we call real gases then. So in real gases, there are a few things that we actually had to assume, okay, in real gases versus ideal gases, and that is your kinetic molecular theory. So the paper that I handed back to you right now, if you want to take a look at it, you can. I think most of you did an okay job in that one. There were some things that I may not have understood, but a lot of you got everything in there. So one of the things that was in there which is also a property of gas, is how much volume the gases occupy, right? So there's a lot of empty space, okay, between gas molecules. So that was one thing that we assume, okay, that the gases will occupy all the space, okay? So which means that the empty space we don't account for, okay? The second assumption that I'm going to talk about here when we go to real gases is we say that two molecules do not have any attractive or repulsive forces between them, okay? Remember we talked about the elastic collision, okay? So in here you wrote that. So when you have a perfect elastic collision, it's just boom, okay? You have no energy lost and nothing is happening, okay? And so the net energy loss gain is the same, okay? But in real gases, when you force them into certain conditions, okay, then those forces then start playing a role, okay? And as we go on to further chapters, you will see that there are molecules that will attract or repel each other, okay? So right now you don't feel it so much because they're really far apart, but if you push them closer together, then it's going to start making a difference, okay? So when two molecules start to attract each other, okay, so if there are attractive forces between two molecules, and they're getting closer, what happens to the volume? The volume will shrink, okay, provided that the entire vessel can also shrink, right? Okay, so the volume will shrink. What about the pressure? Do you think the pressure is going to change? That might change also, right? Because if they're too much within themselves, they're not colliding with the walls of the container, okay? And so that might happen as well. And that can be reversed if you have molecules repelling each other, because if they repel each other, then they will collide with the container, okay? So those are the conditions that make ideal gases different from real gases, okay? And so the two conditions that we study, okay, or that make a difference, okay, in there is right here, okay? So the volume of the gas molecules is really not that negligible, okay? And so then you have to account for that. And then the intermolecular forces, this is the repulsive and the attractive forces, okay, that we're talking about, is also not negligible, which means that you have to account for that also. And so then we come to what is called a van der Waals equation, and this is the van der Waals equation right here, okay? So you have the ideal gas equation, which is PV is equal to nRT, and the two properties that are affected between ideal gas and a real gas are pressure and volume, okay? Those two things are affected. So here you have an increase in pressure because of certain forces, and here you have a decrease in forces, decrease in the volume, because remember the volume is not the real volume, okay, of gases. So you have to subtract that. Now it's explained right over here. The term V becomes V minus NV to account for the space between molecules, and the term pressure becomes this much to account for attraction and repulsion forces, okay? And so this is what the equation would be if you were to work with real gases. And this would be the equation you would use if you were doing physical chemistry, okay? So if you go to higher levels of chemistry, then you stop using PV is equal to nRT, okay, at some point, especially if you want to study the actual behavior of gases, and you start using the van der Waals equations, okay? And then so the A and the A and B, these are constants, okay, over here. And so, and of course is the moles, okay? So A, B are constant for different gases. And so you change your equations, okay, to account for all these things. So that is how real gases behave differently than ideal gases, okay? So that's pretty much it, okay, as far as gases are concerned. Here is, of course, the whole list of things that you should know from gases. I think I put everything in here. The stoichiometry that I gave you, that worksheet, the way to approach those problems is look at the conditions first, okay? So if the conditions are given to you which are non-STP, then actually it becomes a lot, well, I think it becomes a lot easier, because then you just use PV is equal to nRT, okay? And then you just don't worry about anything, okay? It's when STP is given, then you start thinking, oh my God, there were some shortcuts there, okay? So even then, if you don't want to think of the shortcuts, don't think of the shortcuts. Just use the PV is equal to nRT, Okay, at that point, you will still get the same answer. Okay, it will just take you maybe 2 seconds longer to do the problem. So, for your stoichiometry, your gas stoichiometry, you're either converting volumes to grams or you're converting grams to volume. Okay, so you're starting from grams of something and then you will be asked to convert one way or another to give you the volume, okay, of something. You did not have so much of volume in chapter 3. Okay, in chapter 4 you did, but that had to do with molarity. Okay, so be careful to separate things out because this exam is on 4 and 5. Okay, so you will, just make sure that you don't get confused when you read the problem. So when you're going from volume to grams, okay, to go to volume, from volume to grams, you still have to go through moles. You go from grams to volume, you still have to go through moles. Okay, no matter what you do, you still have to go through moles. How do you use that? In case of going from volume to grams through moles, you will first do the PV is equal to nRT and find the moles from here. Okay, that's what you will do. Once you have the moles, then you will do the mole ratio. Okay, so after that you have the mole ratio and then you have the grams from there. Good?
I think so.
Yeah. So that's what was question number 3, I think, or 4. Okay, and the one that you were just asking me, the one with the copper. Okay, so
with like the STP, when we do 22.4 liters,
right.
do we just like just put the 24.2 in the equation for again?
Yeah. Yeah. If that's what's being asked.
So would that be the constant?
Yes. Yes. For STP, if you're calculating the number of moles, okay, in there. So I think there is a problem like that in there. So in that case, yeah, for STP, use the volume as 22.4. Okay. All right. Here, going from grams to volumes, here this is easy. So now from grams, you will calculate moles. Then you will do the mole ratio. Once you get the mole ratio to whatever you need, then you will do the PV is equal to nRT to figure out the volume. Okay, from there. And now you're calculating for volume. So initially you're calculating for moles here, and then here you're calculating for volume. That's how it is. Okay. I will give you the constants, okay, in your exam. So if you forget the 22.4, which I know you won't, okay, but still if you do forget it, it will be there for you. The shortcuts that you can use, okay, regarding the STP conditions are when you were asked, say, if you have carbon plus oxygen to give you carbon dioxide. Let's say we have this, equation, and you have 5 liters of this, and you're asked for the volume of this at STP. Okay, so at STP, the most important thing is the mole ratio. So this is a 1 mole, and this is also 1 mole. So if the mole ratio is 1:1, whatever volume you have here is the same volume you will have here, because the mole ratio is 1:1. Okay? If I were to change that, make this carbon monoxide, and this will be 2, and this will be 2 here. So now this is 1:2. So now what will be my volume here? It should be. That's how simple it becomes if you have STP. Okay? All right. Now if there was something else, okay, this is very simple, all right, in there. But if it was something a little bit, like hypothetically speaking, if this was 3 and this was 4, a little bit not so easy to do, okay, kind of a ratio, then you will start, and this was say 2.4 liters, and you're asked for the volume of this, then you would do 2.4 liters times, and the mole ratio. Okay, so this is for oxygen. You have oxygen here, carbon monoxide here, which is 3 and 4. And that's it. That's your calculation, but only at STP. Okay, yeah. So you can take those shortcuts, but get comfortable with it then. Okay, yeah. Anything else?